Next, let's figure out what the direction of the current is. And in order to do that, I've got to look at the way the wire is connected to the battery. Now, it doesn't matter whether you choose a conventional current or an electron current. We've been working with conventional currents, so now what I'm going to say is let's look at an electron current. Well, what's the direction of the electron current going to be? The electron current, the electrons would leave the negative pole, they're going to travel up the wire, and they're going to travel in a direction that is going to come as it passes through the magnetic field, kind of passing through in the direction that's indicated there. So in a sense, the current, the electron current, is going to be traveling towards us, kind of coming out of the page in that perspective. So now let's figure out the direction of the force. Now we're using an electron current, so let's use our left hand. Put your left hand fingers in the direction of the electron current and put your open palm in the direction of the magnetic field. And when you do that, what you're going to see is that your thumb of your left hand is going to point in the downward direction. This wire is going to be pulled down into the U part of this magnet. Now let's figure out what the strength of the force is. The force is equal to I times L times B times the sine of theta, or F is equal to IL cross B. But since the current and the magnetic field are at right angles to each other, then the sine of the angle, 90 degrees, is going to be equal to 1. So in magnitude, the force is going to be the current times the length of wire times the magnetic field. And in fact, you're going to find in 95% of the problems, the angle is going to be 90 degrees. I know the length of wire, 15 centimeters is 0.15 meters, and I know the strength of the magnetic field, it's 1.2 Tesla. But what I don't know is what is the current. And in order to do that, I've got to use Ohm's law to figure this out. Ohm's law says that the current I is equal to V divided by R. And they told us the voltage, it's 22 volts, and they told us the resistance, which is 25 milliohms. This is 25 times 10 to the minus third ohms. So we could figure out the current in this wire. The current in this wire is 880 amperes. That is a huge current. This would have to be one heck of a power supply in order to provide that current. But that's the number that we've got, so that's the number we're going to use. So now let's put the numbers into our force equation. I calculate that the force on this wire is going to be just under 160 ohms, and it's going to be pulled downward. Now, the last part of this lesson deals with what happens when I have two wires that are parallel to each other that carry currents. It turns out that they exert forces on each other, and I have another demonstration to show you. In this demonstration, what happens is that there's a battery that's connected to a switch, and the switch sends electricity through these two wires. If you pull the switch forward, the circuit's in series. If you push the switch backwards, it's in parallel. When the circuit's in series, what that means is that the wires are carrying currents in opposite directions. When they're in parallel, they're carrying it in the same direction. Now notice that when the currents are in opposite directions, there's a repulsive force. If they're in the same direction, it's an attractive force. Repulsive and attractive. In this diagram that I have here, I've got two wires that are carrying currents in opposite directions. Why is it that the force is repulsive in this case? Bear with me a little bit, and let's think about the magnetic field that's caused by the green wire. Let's sketch that using the right-hand rule, and let's assume that the currents are conventional. My right-hand rule tells me that above the green wire, the magnetic field is coming out of the page, but below the green wire, the magnetic field due to that current is going into the page. So this red wire is being bathed in a magnetic field that is going into the page. If you then imagine removing that green wire, then what you would have is something that looks like this. So I've got this magnetic field that's into the page, and now I've got this red wire that is carrying a current. Now let's apply the right-hand rule. If this is a conventional current, then let's think about our XYZ coordinate system. The current is in the minus X direction. The magnetic field is in the minus Z direction. So I'm going to take my right hand, this is a conventional current, I'm going to point the fingers of my right hand in the direction of the current that's in the red wire. That's the current that's experiencing the force that we're considering right now. Then I'm going to open the palm of my right hand and place it so that it is toward the page. Then my thumb points in the downward direction, and that's the direction of the force on the red wire. Alternatively, you could think about the magnetic field that's created by the red wire, and let's figure out what the force is on the green wire. Again, let's go back to our original diagram over here to the left and grasp the red wire with our right hand and our thumb of our right hand pointing towards the left. In the vicinity of the green wire, the direction of the magnetic field due to the red wire is into the page. So now what I'm going to do is I'm going to imagine that I have this magnetic field that is into the page, and I carry this green wire and put it into that magnetic field. So now apply the right-hand rule due to the force on a current carrying wire. I'm going to make the fingers of my right hand point towards the right for this green wire, and my open palm is going to be facing the page. So now what's the direction of the force? The force is in the upward direction. And again, in our XYZ coordinate system that we look at, the current in this green wire is in the plus X direction, the magnetic field is in the minus Z direction, the force is in the plus Y direction, and this green wire is pushed upward. The opposite happens when you have currents that are in the same direction. If they're in the same direction, you get an attractive force. So in these two wires that I've sketched here, I1 and I2 are carrying currents in the same direction. They will experience an attractive force. This orange wire carrying current I1 will be pulled downward. The purple wire carrying current I2 will be pulled upward. And when they're carrying parallel currents, then the force is attractive. What's the strength of that attractive force? Well, let's imagine that we combine the two laws that we dealt with. The law that tells me what's the strength of the magnetic field due to a current carrying wire that was in the earlier part of the lesson, with the force that's exerted on a current carrying wire when it's placed in a magnetic field. So let's suppose that I have these two wires that are separated here by a distance r. Let's find the force on wire 2 due to wire 1. Well, I know that the force that's going to be exerted on 2 due to 1 is going to be the current that wire number 2 experiences times the length of that wire number 2 times the strength of the magnetic field due to the current that's in wire number 1. And I'm going to assume that if these two wires are parallel to each other, the direction of the magnetic fields are going to be perpendicular to the currents. So now, what is the strength of this magnetic field wire 1 creates at the region of wire 2? B1 is going to be mu naught times I1 divided by 2 pi r. So now if I feed that into my equation, what I'm going to see is that the force on wire 2 due to wire 1 is going to be I2 times the length of wire number 2 times mu naught I1 over 2 pi r. And that is an equation that's very much like one that's written in your textbook. I like to think of it this way, and that's the way I'm going to use it to solve problems. Speaking of problems, here is an example. And again, you won't find this one in your textbook. Two wires of a 2-meter long appliance cord, such as a lamp cord or a kitchen mixer cord, are 3.0 millimeters apart and carry a current of 8 amperes DC. Calculate the magnitude and the direction, attractive or repulsive, of the force one wire exerts on another. Hint, the wire carries current in opposite directions in appliances. And you see pictured here is a cord that has a plug at the end of it, much like you would plug into your wall. So now let's imagine that I lengthen this cord a bit. You could imagine maybe that this is attached to some appliance. If it's an 8 ampere current, that's a pretty big current for these cords. If you have just a regular light bulb that's in a lamp socket, you're probably going to have something that's on the order of 1 ampere or less that's flowing in the cord. And they tell us that the currents are flowing in opposite directions. Now I don't know what direction is the current flowing, but I'm going to make an assumption here that they're flowing in this direction. And these two wires are separated by a distance of 3 millimeters. Now let's get the direction first. Let's suppose that these wires are carrying conventional currents. And if they are, then I could actually sketch what the direction of the magnetic fields are going to be. Or I could just look and say, and remember that when currents are in opposite directions, that they are repulsive forces. That's what I'm going to do in this particular problem. The force is going to be repulsive because the currents are in opposite direction. All right, well, let's figure out what the force is going to be on the wire. The force on the wire is going to be I times L times B. Now, I've got to be careful here. The I is the current that's in one wire, and the B is the magnetic field that's due to the other wire. So let's figure out, let's choose one of the wires. Let's say maybe we're going to work with the red wire. Let's let that be the one that we're trying to figure out what the force is on. So let's call red wire number 1, and let's call the aqua-colored wire number 2. So we're going to say the force on wire 1 due to wire 2 is going to be the current that's in wire 1 times the length of the wire, that's wire number 1, times the magnetic field that's due to the current that's in wire 2. And the magnetic field, B2, is going to be mu naught times I2 divided by 2 pi r, where r is the distance between the two wires. So let's figure out the field strength first. B2. I get that the magnetic field strength due to wire 2 at the place where wire 1 is located is equal to 5.3 repeating times 10 to the minus 4 Tesla. So now let's feed those numbers into the other equation. I calculate that there's about 8.5 millinewtons of force, a repulsive force, that's exerted on these two wires. And that's happening all the time. Anytime a wire carries a current, there's force that's exerted on it, and that force causes the wires to be pushed apart. So, reviewing this lesson, we've learned several things. We've learned that whenever a wire carries a current, that there's a magnetic field that's associated with that, and we can calculate what the strength of the magnetic field is from a formula, and we can figure out its direction using another right-hand rule. If that wire is bent into a loop, then we can figure out the direction of the magnetic field by using that same right-hand rule. When I have a wire that's carrying a current in a magnetic field, then there's a force exerted on it, and we have a formula for figuring out what that force is. And finally, if I have wires that are parallel to each other carrying currents, then they exert forces on each other, repulsive if the wires carry currents in opposite direction, attractive if the wires carry currents in the same direction, and we can figure out what that force is. So, for now, that's it.